Okay, so now we have a definition. Let's talk about how do we model the hazard. Okay, now I showed you with a pseudo-Poisson model that we could model the hazard by saying that the log of lambda of t, of the hazard at time t, is a dummy variable for each year, which captures a separate baseline hazard for each year, plus the sum of terms that are the predictors. So for each predictor, I have a coefficient. That's if I use the pseudo-Poisson model. And this is a proportionate hazard model, because the effect of every single variable, like this one, is proportional not merely to the baseline hazard in that year, but to the effect of all the other covariates. Because if I exponentiate the left and right-hand side of that equation, I see that I get E, that the hazard is the exponential of the dummies for each year times e to the BP xp. So the effect of x sub p of this particular predictor that I may be interested in multiplies the effect of all the other predictors. And that's what proportionate means. Now, the baseline hazard by this definition is the value when every one of the x's is 0. And this comes back to a theme that I've mentioned before, which is it is important to center some of your variables. If I recruit a cohort, a reasonable predictor to have in my regression model for your age at death is your age at entry into the cohort. Because if you were 60 years old at entry, you couldn't have died at 55, right? So it has to be a predictor, okay? Age equals 0, that means the baseline hazard is the instantaneous spontaneous abortion rate? I mean, that would not make a lot of sense. So it's important to take variables where setting them equal to 0 would not make a lot of sense and center them, subtract their mean. So now the baseline hazard in a particular year is the baseline rate of dying for a population at the average age of entry of the people in my cohort. Okay? Otherwise, those things aren't going to be terribly meaningful. Now, you may not want them to be meaningful. You can say, I'm never going to look at what the coefficients of those dummies are. But if you ever do want to look at how the hazard varies over time, how the baseline hazard varies over time, center your variables. So now the Cox proportionate hazard model, the difference is not that it's a proportionate hazard model, so is the pseudo-Poisson. The difference is the baseline hazard. So the Cox proportionate hazard model is almost identical except that instead of putting in dummy variables for each year to capture how the baseline hazard varies over time, I put in some function of time. Okay. Well, dummy variables for each year is a function of time. This is a function of time. What's the difference? Cox doesn't tell you what that function is. He's going to let it be estimated non-parametrically, and in fact, what he showed is that you could get unbiased estimates of your parameters of interest, the coefficients of the predictors of mortality, without estimating it at all. Because he found a way to factor the likelihood, the probability of dying, right, given the covariates and the baseline hazard, in a way that he can factor out the baseline hazard and get a part that doesn't depend on it and maximize that. Find the coefficients of the predictors that maximize that partial likelihood, and you don't have to worry about what lambda naught of t is. It could be any funky thing, and it doesn't matter. And again, for a general population, that may not be terribly useful, but if you start looking at cancer patients, people who have congestive heart failure, other people, you can get some strange distributions of what the hazard rate is. The hazard rate after a myocardial infarction is very high. It declines quickly for the first month, and it declines more slowly for the next year. It does things that maybe I don't want to make my inferences about my predictors based on how well I model that. If I can make that cancel out, that would be great. Okay? And so that's what Cox's approach does for us. And I'll show you how that cancels out in another talk. But the point is, I do not have to specify some function that describes how the baseline hazard varies. It can be, I just say it's some non-parametric function, and I don't care what it looks like, because I can estimate my coefficients without knowing it. Now, Cox's model still does assume proportionality, namely that the effect of every variable is proportional to the effect of every other one. But we saw that that was not true, for example, for cancer mortality in men and women. So the difference between men and women here and the difference between men and women here are not the same. Men have higher cancer death rates than women, but the ratio between them isn't constant. But a proportionate hazard model says it is. If I had a coefficient B for the effect of sex on the risk of dying of cancer in my regression, and let's say when I exponentiated it, I got 1.2. That says men die at 1.2 times the rate of women. That proportionality is 1.2. But that's not true here. The ratio of this to that is bigger than the ratio of this to that, because mortality rates have been declining faster for men than for women. That's what non-proportionality means. Means the ratio of the rates in the two groups is changing. It's not some fixed constant. And that's something you need to deal with in any proportionate hazard model. One way to do that is to fit a separate baseline rate for men and women. So I could fit a model where now the log of the hazard in any given time is there's a log of the hazard for men times a variable that's 1 when males equal 1 and 0 otherwise. So that disappears when I'm looking at a woman in my cohort. So the log of the hazard is the log of the baseline hazard for men when male equals 1 and otherwise 0, male if I'm looking at a female in my cohort, and that goes away, in which case it's the log of the hazard in women times female equals 1, and then I assume that the remaining variables have proportionate effects. So again, for example, that the effect of diabetes on death rates is to multiply them both by the same ratio for men and for women. Again, let's say diabetes increases your risk of dying by 1.15, then I take 1.15 times the risk in men and 1.15 times the risk in women, but that baseline risk in men that gets multiplied by 1.15 can be a different number than the one in women. Okay? So that's how we deal with the lack of proportionality. So one last thing I'd like to say is, remember in the beginning I said we didn't observe all the failure times, right? Some of them are censored. All of these methods still require us to assume that those missing failure times are missing at random, conditional on the covariates. That two people with the same age, same gender, same smoking history, etc., if one of them I observe the failure time and the other I don't, that's not predictive of what the actual failure time is in the unobserved person. And if that's not true, all of these things will give us erroneous inferences. So, to summarize, we've defined what a hazard is. It's the instantaneous rate of dying. We've defined what a survivor function is. We've looked at two different ways of defining a baseline hazard, parametrically, with a dummy variable for each year, or a linear time trend for year, or non-parametrically in Cox's model. We've talked about the assumption of proportionality, and we've developed a model that allows us to try to predict how various risk factors affect your chance of having an event, of failing at a given time. Thank you.